Hey folks, in lesson 16 we're going to start moving toward the idea of using energy to solve our dynamic systems. So just as a review, we started out using F equals ma to solve equations of motion. We would take Newton's second law, develop the kinematics, find the force on a particle, and then from that we would then integrate to get our state. And so with that would give us everything we needed about the trajectory. In the last section, what we did is we then took F equals ma and we converted that into momentum. And so we came up with this relationship that was based on the idea that we're going to take our force and we're going to integrate that with respect to time, and it gives us a change in velocity. So what we were essentially doing is ignoring acceleration and saying that we can get the change in our velocity, whether that's a change in speed or it's a change in direction, and relate that to the force that occurs between time 1 and time 2. This gave us some useful tools in which we could take a system at a particular time, relate it to a system at a different time, and we could really just ignore what happened in between in a lot of ways. But a key item to remember is that we were always using F equals ma. So there's nothing different about this equation from Newton's second law. So now what we're about to do is we're now, instead of integrating force with respect to time, like what we did in momentum, we're now going to integrate our force with respect to the path. So this is completely dependent upon the direction that it's going and the path that the particle is taking. So what we're going to do is introduce this idea of work. It's going to be a rigorous treatment of work, and that's the integral along the path, of the integral of the force along the path. And then we're going to apply this in an F equals ma setting to understand how work and power relate to each other. They're somewhat counterintuitive in some ways, and I think it's simply because of the vernacular that we use. We don't always use the word power correctly. We don't always use the word work correctly. And so by the end of this, through this example, we're going to apply this to an electromechanical system and get an idea of what we're doing. And then in the next lesson, we're going to develop some tools that simplify a lot of this. Well, they simplify dramatically so that we can use this in the context of energy. So let's start out with our definition of work. Work being defined as the amount of energy that it takes to move a particle along a path. And so to move something along a path, it has to have a force, or to accelerate something along a path, it has to have a force applied. So work is based upon this idea that we're applying force to a particle. So let's do that. If we apply a force here, and there's our force Fp, then what we're doing is that we're moving this along this path trajectory. And so this trajectory of particle P, we'll call this gamma sub P. And then the path itself is determined by position vectors. So we have a position vector from O to P. And so this is r, p with respect to O. And if we're moving this along the path, then what we can do is we can take our force and then we can dot it with the path itself. And so the path itself is coming about in incremental steps. And so when this particle P moves a certain distance, then what we've done is we've created a new position vector. So this is what we would call r plus dr of P with respect to O. And so the difference between that initial position and that final position, or that next position, is dr of P with respect to O. So it's an incremental change in the position of the particle itself from its initial point to its next point. Now we haven't referenced time here. Of course, time has passed, but what we've done is we've just said the force is applied to this particle and it's along this path. Now a couple things to note is that this force, we haven't drawn this along the direction of the path, or the direction of dr, and that'll come up later. But so that means that there has to be some sort of constraint that's keeping this force along this path. And one more thing to point out about this is that because we're looking at a change in position, if you recall from the very first week, when we're looking at a change in position, it matters where we observe this from. So that means in anything that we have a dr we also need to indicate what reference frame we're viewing that change in position in. And so, the math that we're going to apply here is the dot product between the force and then the change in position. So what that gives us is the force applied on particle P dotted with d, or a change in our position vector, as observed in the inertial reference frame. And so now we have a relationship that we can integrate, and when we integrate this along the path, so this is a path integral, we integrate this along the path, we get the work that's being done by the force as applied to particle P to move it along that path. So a couple of important things to notice about this quantity here is that it's a dot product. And so if it's a dot product, we also call that a scalar product. So that tells us that work is a scalar. It's not a vector. Momentum was a vector. Angular momentum is a vector. Linear momentum is a vector. But work is a scalar. That's the first thing to observe. The second thing is that when we dot these together, and we have our force dotted with our change in position, then that tells us that work is only done by forces that are in line with the motion. So work is done by forces in line with the motion. And so by implication, work isn't done by forces that constrain the motion. So if we go back up to our diagram here, the work that's done on this particle to move it in this distance, dr, from this point to that point, is only being done by the component of this force in that direction. Likewise, if there's a constraint force here, and you can see with this curvature in this direction, with a centripetal acceleration pointing inward, meaning that to maintain or to create that centripetal acceleration, we need to have a constraint force pointing in this direction. Work is not done by the force that's in that direction. That's perpendicular to the path. So, another thing this allows us to do is use path coordinates to determine work. So with our path coordinates, we have two vectors that we traditionally use. We have an E sub t, which is our tangential vector, which is pointed in the direction of velocity. Then we have our E sub n, which is our normal vector. So force in the en direction does no work. Force in the tangential direction always does work. The next item to note is the direction of the work, or the sign of the work. So the sign of the work, positive or negative, so positive or negative sign, depends on whether the force is going to promote the motion or it's going to hinder the motion. And so if the force is promoting the motion, so it's in the direction of this incremental distance, then we're going to get a positive scalar value. And then if it's in the opposite direction of that incremental distance, then it's hindering the motion, and we're going to get a negative scalar value of the work. So let's take a look at this formal presentation of work. And so we've already taken care of the right-hand side. The right-hand side saying that work performed on P by a force Fp is simply going to be the force and how we characterize that force, how we model that force, whether it's a spring force, whether it's a friction force, whether it's an external force, our different models, or a viscous force. Then we're going to dot that with the change in position. We have to observe that from an inertial reference frame. We have to not only state the frame, but in this case we always need to do this with respect to an inertial reference frame. And so that is our definition of work when we take the integral along the path, or along that trajectory, gamma p. And so look on the left-hand side, and we do have cumbersome notation for this. But it tells us a lot. So when we read this, we have the work on particle P, and it's the work on particle P, and this subscript is saying that it's performed by this vector, this force vector, F sub P. And then in the parentheses, what we're saying is that it's a function of two things. It's a function of the position vector that's following the path gamma p. So that way, when we're characterizing the work on a particular particle, it's very clear what the position vector is and what path it's following and what's doing the work. So just break this down into its individual components as you're getting used to this notation that we'll use. And I mentioned earlier that we can put this into the path frame using a path integral. And in the path frame, we have the same left-hand side. So to reiterate, this is the work done on particle P due to the force F sub P, or whatever force it is. And then it's a function of the position vector that's traveling along the path. And this is equal to that force dotted with, and this is really nice, it's going to be that force dotted with the basis vector in the tangential direction, because remember the normal direction is our constraint force or our constraint direction, and that drops out. And then the integral is a path integral, and it's a scalar integral. It's not a vector integral like what we had earlier, but it's a scalar integral, so it's along that path. And because this is dependent on path, this reinforces the idea that work is going to change depending on the path taken, or most likely it'll change depending on the path taken. So how you get from point A to B, let's say in this case getting from the initial position to the next position, is going to change the amount of work done. And so here, if we take the path from that point to that point, that's probably going to give you a different work than if we take the path of something like this, and then finally end up at that point. And the reason why is because we're integrating force with the change in path, and so the force to get around this path over that particular time, over that particular distance, is going to increase the work. So if work is the amount of energy that it takes to move a particle along a path, then we need to be able to characterize the ability to do that. And so we do that by using power. So power is quite simply the change in work over time. So we end up with the units of energy per second, so it's joules per second. And as work is being done, then we're developing power. So we're doing work and we're developing power as we do that. So the ability to do the work is now dictated by power. So for example, a more powerful motor can do more work at a faster rate, or can do work at a faster rate than a less powerful motor. And we'll see that in the example that we're going to do, or in how we size motors. And so this is simply the force vector dotted with, looks like I forgot my dot, dotted with the velocity of P with respect to O as observed in the inertial reference frame. And so power also is a scalar, and we write that as the power on particle P created by the force that's applied to particle P. So let's demonstrate work and power and the differences between two different force profiles that we could apply to a simple, very simple system, and try to gain some intuition about this. So what we've got here is a mechanical system in which we're lifting a mass P, using an electromechanical hoist or a motor, and we're going to go from the ground to a height h. And so what we can do with this is we can set the force profile in any way that we like, but we're still going to move this mass from 0 to h, and we'll compare the two between, so what the work is and what the power. So let's define our reference frame. And for our reference frame, we have an inertial reference frame, and we're always going to use an inertial reference frame when making these calculations. And so it's an inertial reference frame with a fixed point O that has the basis vectors E sub 1, E sub 2, and E sub 3. So E sub 1 to the right, E sub 2 pointing up, and E sub 2 is pointing in the direction of our travel of our mass. So we define the position of the direction, or the position of our travel, using the coordinate y. And so this means we simply have a straight line system in which we have y, and then attached on the other side of the pulley is a tension T. The kinematics of the system are quite simple, where we say our position vector is equal to y in the E2 direction, our velocity vector as observed in the inertial reference frame is equal to y dot in the E2 direction, and then our acceleration as observed in the inertial reference frame is equal to y double dot in the E2 direction. We're going to apply F equals ma, so we need to determine our force. And so our free body diagram on this system is going to be mass times gravity in the negative E2 direction, and then we have our tension in the E2 direction. And so our force applied to this system is T minus mg in the E2 direction. And so F equals ma gives us T minus mg in the E2 direction is equal to y double dot in the E2 direction. And we need to have a mass on the right side as well. Alright, so here's our equation of motion. We haven't done anything new yet. This is simply defining a reference frame, defining our kinematics, applying Newton's second law. So now we want to apply one of our force profiles and calculate both the work and the power on that and compare that to another force profile. So let's talk just a moment about developing these force profiles. The two different approaches that we want to take for hoisting this mass are going to be what's called a jerk hoist. We'll do it first. And then a constant velocity hoist. And to apply these, we need to come up with a model of our external force. Now this is new for us. We haven't actually prescribed external forces before. We've just said we've got this particular motion, we've got a particular force, and we really haven't said anything about the profiles of those forces. So for a jerk hoist, this profile is saying that we're going to have our max force at the very beginning of the lift, and then we're going to decrease that force as we go until we're just only holding the mass at the top. So what we can do is we can say, if on this horizontal axis we're going to go from 0 to our height h, then how our force looks, which we'll put on the vertical axis, is that we want to start at a particular force, and then we want to decrease the force linearly until we get to the height. And so at the very end of the lift, we still want to be holding up our mass. So that means that the force at the end of the lift needs to be equal to mg. That would be the very end. And then we've got a difference here between where we end up and where we started, and we'll call that mb. Or rather, the difference between these we'll call mb. So our beginning force will be mg plus mb. So we've simply said that we've got a place that we need to end up, which is mg at the very end to be able to hold it, and then we're going to add this difference that we're just parameterizing by this parameter b. And so we're saying that the force, or the tension, at position 0 is equal to mg plus mb, and that our tension at our height, when we get there, is going to be equal to mg. So let's write out this model in slope-intercept form, where we say that our tension is going to change as a function of our height, y, and this is equal to that change, dt dy, multiplied times the height, plus our initial tension. We see here that our slope, dt dy, is going to be equal to negative mb over h. And so when we plug in our slope, negative mb over h, and we plug in this intercept value, which is mg plus mb, then we get the equation for this just linear change, is our tension as a function of y is equal to mg plus mb multiplied by 1 minus y over h. And so now we've got a linear model for our force that we can change our slope however we'd like. You know, this doesn't have to be a negative slope. We can increase our slope, or we can keep our slope of our force flat, keep it the same. So now, given this profile, we can plug this into what we've said is our equation of motion, now as a function of y. And when we plug this in, we get the following, where our tension is mg plus mb multiplied times 1 minus y over h. It's our tension model. And then we subtract mg, and this is all in the E2 direction, and this is equal to my double dot in the E2 direction. So what we see here is that mg cancels with mg, and so our equation of motion for this system, based on this force profile that we have, is y double dot is equal to b times 1 minus y over h. So this is our equation of motion. And while we're at it, let's solve this equation of motion. This is a second-order linear differential equation, and so we can show that a little more clearly in a form that we typically like by saying that we rearrange our terms. Y double dot is equal to b minus b over h multiplied times y. You see now that it's a linear differential equation, and we put this into the form that we like to use, which is y double dot plus b over h multiplied times y, and then this is equal to b. So there is a forcing function on this, and we're going to have to get a particular solution. And so linear second order differential equation. And so one thing we can do is we can simplify this so that our constant is easier to deal with, and we can get y double dot plus omega naught squared times y is equal to b. And so this is where omega naught is equal to the square root of b over h. We have boundary conditions to apply to this. So if our mass is starting at rest, so y at height 0 is going to be equal to 0, and then y dot is going to be equal to 0. It's starting at rest, and then also we're starting at 0. And so when we solve our differential equations, then we get the form y dot at time t is equal to the square root of b times h sine omega naught t, and then we'll get the position y is equal to h multiplied times 1 minus cosine omega naught t. And then here are the solutions of our differential equation. But before we move on, let's examine these profiles, because right now if you just look at these equations, you say, oh, it's got a sine, it's got a cosine, I'm not really sure what that looks like, or I imagine some of you are. So let's just take a look at it and be sure that we understand this. So for our position, let's start with our position. What we have here is we've got a position in which we're starting at 0 as our y, and we're going to increase that until we get to h. So that means over the time, we're going to go from 0 to h in some way. So when you look at our expression here for position, the only way that y as a function of t can be h is if cosine of omega t is equal to 0. That's the only way that that can happen. And the only way that cosine omega t can be 0 is going to be at the time, or at the point rather, in which, so y is equal to t when omega t is equal to pi over 2. So that means on our time axis, we're actually looking for the point, or let's call this the omega t axis, is equal to pi over 2. And of course we can solve for time and say that on the time axis the height is going to be reached when time is equal to pi over 2 times omega. And so that profile looks like, because it's a 1 minus cosine, the profile is going to look like this, in which we hit the apex of this function at this time. So let's take a look and see how our speed changes at that same point, which omega t is equal to pi over 2. And so if omega t is equal to pi over 2, then this tells us that sine at that point is going to be equal to 1, and so our speed at that time is going to be equal to the square root of b times h. At that height h, and our profile looks like a sine, and there's its apex as well. And so what we see here is that we're starting from rest, we're starting at a speed is equal to 0, and we're increasing until we get to h, and that's going to be the square root of b times h, and then our position profile starts at 0 and then increases until h, both in a sinusoidal manner. So let's create the work and the power, so the work done by the jerk hoist as well as the power developed by the jerk hoist. So for our work, we're saying it's the work done on particle P, and it's done by the tension, which is a vector, and this work is a function of our position vector P with respect to O, and it's along the path gamma P, and this is equal to the integral of that tension dotted with our change in path as observed in the inertial reference frame, and that's along the path gamma P. Now the reason why we can calculate this using this integral is because we have our force, our tension, that's very well defined, and we also have our path that's very well defined but also very simple. So these two components that go into this are our tension vector, which is equal to mg plus mb multiplied times 1 minus y over h. This entire quantity is in the E2 direction. And if we write that out in a easier form, it's mg plus mb minus mb over h times y. Keeping our vector notation, that's in the E2 direction. And then our d r p with respect to O, as observed in the inertial reference frame, is equal to y, which is our change in position in the E2 direction. So the fact that we know our force completely throughout the entire range of motion, and then that our incremental position is very easy, allows us to make this calculation. So let's make it. So setting up our integral, we're saying it's the integral of mg plus mb minus mb over h times y, and then it's dy, because we're taking the dot product of this term and the dot product of that term, so it ends up being an all scalar notation. And then our integral we're calculating from 0 to our final height h. And when we integrate these pieces, we get mg plus mb times y minus mb over h, y squared over 2. That entire quantity will be evaluated from 0 to h. And then by doing the algebra, we get our final quantity of mh, and it's g, and then it's plus b over 2. And so here's our scalar value for the work done on particle P along the path gamma P, which is simply a vertical line in this case. Let's make one quick comment on this, in that when you've seen work before, whether it's in high school or perhaps university physics course, that you've seen typically done in the presence of a constant force. So this is a more complicated situation because we're varying our force. But notice that if you did a constant force, and let's say it was the force of gravity, then this work would end up being, simply mh times g, because gravity is a constant force going down. And if you were going to oppose that force with a constant force to bring it up, then of gravity, which we'll do in a moment of the constant velocity, you're still going to get an mhg. But in this case, we've got that term, mhg, but then we have an additional term, which is the mass times the height, multiplied times this other factor, which is b over 2, which is the change in that force over that time it takes us to lift the box. So just take a look at that, keep that in mind, because we're going to make a comparison to that next condition. So next let's calculate the power developed. And so that's the power developed by applying this tension onto particle P. And this is a function of time. Most of the time we don't, as you know, we just drop the as a function of time when we're typically writing things. But this is going to be our tension dotted with our velocity of P with respect to our inertial point as observed in the inertial reference frame. So we'll pull each of these components in, where our vector tension is mg plus mb minus mb over h multiplied times y. And this is in the E2 direction. And this is where y as a function of t, we've already solved for this. Y as a function of t is equal to h times 1 minus cosine omega naught t. We already have our velocity of p with respect to o, which we said is y dot, and we've solved for y dot, and so y dot is equal to the square root of b times h multiplied times the sine of omega naught t. And so when we put all these together, we get an expression that says the power developed by applying this tension to point P as a function of time is equal to mg plus mb cosine of omega naught t, and that's the entire quantity multiplied times the square root of bh multiplied times sine of omega naught t. Now once again, it looks like a complicated expression, but let's take a look at its individual parts and actually see what that curve looks like. So we can rewrite this as the power on point P due to this tension is equal to, and let's just factor out our common terms, where we say our common terms are mg, the square root of bh, and then let's just deal with what's in the middle of this, where we'll have a sine function, so it's sine of omega naught t, plus a combination of these two functions, so b times sine of omega naught t multiplied times cosine of omega naught t. Now let's look at those individual terms. So first, we've got a scalar, and so we can just ignore our scalar for right now. And if we ignore that coefficient scalar, then we've got sine of omega t. And sine of omega t is something that we understand pretty well, and we're only evaluating this across an integral, or across the interval from O to, and if we're on this omega t axis, let's make it easy, from 0 to pi over 2. Just how we set up our last pieces. And so sine gives us a function that starts at 0 and then creates its height, or its tallest point, at pi over 2. Now let's take a look at the second piece, which is sine multiplied times cosine. So at our points O, At O, this is equal to 0 because sine is equal to 0. And at pi over 2, it's equal to 0 because cosine is equal to 0. And then in between those, it's going to be a trade-off between the two. And we'll get a function that looks like this, which has its apex right in the middle at pi over 4. And so what we're doing is we're taking each of these terms, we're adding them up. And so if we add up sine, and we add up sine times cosine, and generally, we've got these coefficients that are applied there, then what our function looks like for our power of p, so this is p, that's developed by the tension T, is we're going to add these two guys up, and our power looks something like this. And so you can see that from the point at which we begin, O, up until the final time, or until that height's reached, we have 0 power, and then we hit the increase of the power, or the apex of the power, somewhere before the end, and then trail off at the end. And so that's what our power profile looks like. This is the power generated by hoisting the mass using a jerk hoist. And when we're sizing that motor, it's going to be the power, this peak power is going to be the power that we need to be able to produce with that motor. We have one more quick situation to run through, and that's if we have a constant velocity hoist, which is pretty typical. And so constant velocity is simply saying, as you might imagine, that our acceleration of point P as observed in the inertial reference frame is equal to 0. So when we plug this in, all of our forces are equal to the mass times acceleration. Then what we get is our tension in the E2 direction minus mg in the E2 direction is equal to 0. So that's going to give us that our tension that we need to create a constant velocity is going to be equal to mass times gravity. And so think about that just a moment. So if we've got a constant velocity, then that means that we're not starting at rest. And this is an important point to discuss right here very briefly, is that all the tension that we need here is to just oppose gravity and to maintain that velocity. So one thing that we're ignoring here is how we got that velocity in the first place, which, recall from the last chapter, we got that using an impulse. So right now we're ignoring the work due to the impulse, which we'll take care of in a couple lessons. But right now we're only looking at the work done given this initial condition. So nothing's changed in our work formulation except for our force, where our force P is going to be equal to our tension P, and that's equal to our mass times gravity, and that's in the E2 direction. Our incremental step is the same. That's going to be y in the E2 direction. And then we put all this together. We get the integral from O to H of mg in the E2 direction dotted with dy. Oh, that should be dy. dy. And this gives us the work is equal to mgh. So the only force that the hoist is applying is a force opposite of gravity. It's given an initial velocity, and so the only work that's done is mgh. And so immediately you see that the work done by a constant velocity hoist in this condition is less than the work done by the jerk hoist, which has a higher force at the beginning and then comes down to the force mg. So now let's calculate power done by the tension T as a function of time, and this is going to be the force due to the tension dotted with the velocity of P with respect to O as observed in the inertial reference frame. And so our tension vector is mg in the E2 direction. And then if we want to compare these two together, then we need to create a velocity vector that's going to work in the same amount of time. So let's come up with an average speed. And so that average speed, we'll just call that v. Our final speed is square root of b over h. And this is going to be divided by the change in time. And so our change in time, so it's square root of bh, and our change in time that passes is pi divided by 2 omega naught as defined by that jerk hoist. And then our average speed ends up being 2 divided by pi multiplied times the square root of bh. So that's our average. And so our velocity, being our average speed in the E2 direction, is equal to 2 over pi multiplied times the square root of, and that's in the E2 direction. And so the power developed by the tension in a constant velocity as a function of time actually isn't a function of time, because we've got a constant mg and we're in the E2 direction, and we're dotting that with a constant in the E2 direction. And so our final quantity ends up being 2mg divided by pi multiplied times the square root of bh. And so over time we have a constant power throughout the entire cycle. Alright, let's make a comparison between these two hoists. We've got our jerk hoist and we've got our constant velocity hoist. So we'll put our jerk hoist in black, and we'll put our constant velocity. So let's make our comparison between the work done in each of these hoists. And so we have our jerk hoist, our first approach, in black, and then our constant velocity in red. And we've already pointed out that the jerk hoist is going to be mgh plus this term, which is mh b over 2, and then the bh defining part of the differences in our initial force, and then our total work in the constant velocity is just mgh. So we have less work that occurs, or that's done, in the constant velocity hoist. We can get an idea of why that's the case by pulling in the force profile from the book. And here we see our jerk hoist on the left-hand side and our constant velocity hoist on the right-hand side. And so for our work, which is going to be the force dotted with the change in position, see here on the jerk hoist we have a high force that decreases over time. That high force results in a large increase in the height that has a decreasing change. Whereas the constant velocity hoist, we have a constant force profile in which the change, there's a change over time, which is, was on the wrong side, sorry, a change over time which is constant. And so that constant change over time with a constant force, as you already know, gives this mgh, or the force times the distance. So in high school, you were taught this as this is just force times distance. Here, we've got this force times distance with this extra term that occurs due to this decreasing force, but as well as this changing change in our height. Now let's take a look at the power developed in each of these hoists. So for the jerk hoist, we calculated that the power developed is like a sine with a little bump in the middle of it, in which we have a power increase and then a slight decrease. And in the constant velocity hoist, the power is constant throughout the entire time that the motor is lifting the block. We said earlier that it's this power developed, or the ability to develop this, the ability to do work, is how you need to choose your components. So in this case, we need to be able, in this jerk hoist, to get more power out of the motor to be able to accomplish that last part of the lift. And in the constant velocity hoist, our power is lower, much lower and consistent to obtain or to be able to accomplish that work. So if we're using this, we could size that motor smaller. The motor doesn't have to be quite as powerful. But one of the things I want to point out is, where does increase in power? Where is the power demands that are going to be on the motor? And in this case, look at this. The power demands, the high power is toward the end of the motion. Now this, if we zoom back out and look at our motion, we have a high power demand which occurs when there's a very small change in position. Okay, so this is a counterintuitive part of this, which is important to note, in that in this part in which this jerk hoist is applying a really high force, this is not the part in which you need a very powerful motor. You need a very strong motor, but you don't necessarily need a powerful motor. The power actually is needed out here where the velocity is higher. If we look at our velocity chart, where our velocity is higher and we're still trying to increase height above the ground. And I think sometimes this counterintuition comes from our misuse of the terms power versus load. And so here's what you want to think of, is that if you're driving in your car, then is it easier to increase your speed if you're going slower or if you're going faster? And the answer is that it's much easier to increase your speed or accelerate if you're going slower due to, let's just say if you're in first gear the entire time, if you're in your manual transmission, then you're able to generate more torque lower at that lower speed than you're able to, and speed that up, and the same torque that you would generate at a higher speed is not going to have as big of an effect. And so that's power. The ability, because power is based on speed, power is the ability to generate speed because it's the work that you do over time, and being able to do this last little bit of work in that second part of that with that jerk hoist requires a whole lot of power versus the last bit of work, in this case, doing a constant velocity because the speed is lower. Alright, so sit on that for a little bit, think about that. We'll talk about that a little bit more in class and try to understand this. And so these are the basic concepts of work, which is energy. Remember the units of it are joules, and power, which is the development or the ability to do work, and we develop power. And so what we're going to do next time is we're going to put these in terms of only energy, and it gives us some nice tools to use to solve dynamics problems. All right, that's the end, and I'll see you in class.